I'm going to tell you today about some recent work I did with my collaborator Anish Manohar on a classic problem. Anish has been fantastic to work with, and I've learned a lot about EFTs working with him on this project and discussing other physics. I'm going to tell you about our results on the RG improvement of the effective potential of quantum field theory in cases where I have very disparate mass scales. So you would think, in the way I've phrased that this is just some classic EFT problem that must have been systematically solved, but I'll explain throughout the talk, there are some important subtleties to getting this right that explain why we have something new to say about this. So I'm going to get started. So I'm going to begin with just some general introduction and motivation. So maybe call this QFT 101. So the effective action in quantum field theory is a fundamental object that we know and love. It is computed, I'll remind you, by doing the path integral over the fields in the presence of external sources. And in particular, it is a function of classical background fields. All of the fields have been integrated out in the path integral. And so these classical background fields, I'll denote them with a hat. And these are the expectation values of the fields in the presence of the external source. And generally speaking, when I say phi for fields, I have scalars in mind in the context of this talk. We're going to, for most of this talk, just restrict to scalar theories just to make our lives simple. Now, the effective potential is the value of the effective action on constant background field configurations. So I'll remind you, it's the first term in the derivative expansion of the effective action, which I've written here. I think you can see my mouse. And the effective potential plays an important role, as we know, in determining the quantum corrected vacuum of a quantum field theory. So in particular, the value of the background field that minimizes the effective potential is the expectation value in the true ground state. So if I minimize the all orders effective potential, this is the true expectation value in the vacuum of the theory, and the value of the effective potential at this point is the energy density of the vacuum. So therefore, this implies important applications for spontaneous symmetry breaking. So this goes back, for example, to the foundational work by Coleman and Weinberg on this subject in '73. So they looked at massless scalar QED, so QED, and I have some massless scalar with a lambda phi 4 interaction. And they showed that radiative corrections to the effective potential shift the ground state from the classical minimum at the origin to the spontaneous symmetry breaking minimum away from the origin. Now, so the effective potential is a very powerful object if we can compute it. And it has a well-known loop expansion, which goes back to the original work by Coleman and Weinberg. And so the loop expansion is an H-bar expansion, and the tree level piece is just the tree level potential and the Lagrangian evaluated on the background fields, the phi hat. Then the one loop piece has a well-known formula, which I've written here. And so I'll just point out some features of this formula. So first, it's a function of the eigenvalues of the mass matrices for the scalars, fermions, and vectors in the background of the defined by the phi hat. And so, for example, this ms squared that appears in the scalar terms, these are the eigenvalues of the second derivative matrix of the Lagrangian in the scalar sector. And all of these masses in particular depend on the values of the background field. So they depend on the background fields. So then this takes the form of m to the 4th log m squared over the different sectors in the theory. And I've given this formula on this slide in some particular scheme. So I'm using MS bar scheme here, and different scheme choices would change these constants, the 5/6 and the 3/2 in these terms, for example. And the other thing I'll point out is that here the renormalization group scale at which I'm defining the theory appears in the logs, in the log m squared over mu squared pieces. And so this is this is a fixed one loop order formula, and so the RG scale appears here. So just for example, to go back to this massless scalar QED example, in this case, these masses go like phi hat squared. These mass squareds go like phi hat squared. So what happens is that when the lambda phi 4 coupling is goes like the 4th power of the gauge coupling, so when I have this particular scaling, but I could still have these couplings be small, then a one loop term from this one loop potential can balance the tree level lambda phi 4 potential, and this is what leads to this nice spontaneous symmetry breaking feature that we saw on the previous slide. So let's take a step back. I just gave you a fixed one loop order formula, but more generally, we can look at the perturbative structure of the effective potential. And so here, I'm going to denote by lambda, just the generic set of couplings in the theory. So depending on what theory I'm looking at, maybe I mean like the mass squared, some cubic coupling, quartic coupling, etc. And by L, I mean the set of logs in the theory that go into the Coleman-Weinberg formula. So these mass squareds, these log mass squareds over mu squared. And so if I just denote the tree level piece by a 1, then relative to tree level, the n loop pieces will have a lambda to the n, and then a series of these logs that we saw in the previous slide at one loop, where at leading log order, I have a log to the n, and then I have subleading powers of logs. And so evidently, of course, this is standard, evidently fixed order perturbation theory will break down when lambda log is very large. So when these logs are large, then it is no longer reliable to truncate the loop expansion. And so in such a case, we can restore the validity of perturbation theory by RG improving the effective potential, which we do by running to a scale where perturbation theory is reliable. So the effective potential is RG invariant, and this formula I wrote here is just saying that if I run the couplings in the theory with their beta functions and also this background field phi hat, it might have an anomalous dimension, so I should take that into account. Then the result shouldn't depend on which mu I study the theory at. And so then I have the standard result that if I integrate the one loop renormalization group equations, I can sum this leading log series. If I integrate the two loop RGE, I can sum the next to leading log series and so on. So in problems where I just have one mass scale in the problem, then this RG improvement procedure was spelled out back in the original work by Coleman and Weinberg. And in such cases, I can RG improve basically by running to a scale of order the mass in the problem. And so if I just have one mass scale, then then by doing this, the log is small, and we're done. So in the Coleman-Weinberg example of massless scalar QED, I said that the masses both go like phi hat, like the background field. And so if I run to a scale of order phi hat at the minimum of the potential, then the logs are small, and I'm done. Of course, in a generic situation, I have multiple scales, and in particular, if I have some multi-scale problem where I have multiple disparate mass scales in some hierarchy where one is much larger than the other, so I have some heavy scale that's much larger than some light scale. Then if I take the RG scale, if I want to run to either the heavy scale or the light scale, either way, I'm going to have large logs that go like log of the light scale over the heavy scale. And so this is a generic problem, and it's a typical EFT problem. So this is the typical setup for an EFT problem. And maybe somewhat surprisingly, at least surprisingly to us, this problem hadn't been systematically solved. So what I mean is that the systematic renormalization group improvement of the effective potential in such a multi-scale case had not been completely solved. And so this is what we sought out to do. And so our result can be summarized in that we sum the leading log series in the effective potential in such a multi-scale case with the hierarchy of mass scales. So we're going to sum this leading log series, and I also want the whole one loop result. So we're also going to get this +1 here at one loop. And so our approach is, of course, based on the typical EFT approach. So in particular, we're going to introduce a power counting. So say I have some small z, and z is small, and it goes like the light scale over the heavy scale. And I'll construct some series of EFTs by integrating out heavy particles. The actual, what this power counting is exactly will depend on the theory that I'm looking at. So I'll be more specific in examples soon. And so the broad strokes idea is just the completely standard EFT story. I'll start with I'll start at some heavy scale, some high scale, so some mu that goes like the heavy scale, and then I'll integrate out the heavy field and match onto an EFT that depends on the light field. And then I'll run in the EFT from the heavy to the light scale, and this running will sum if I run at one loop, then I'll sum the leading log series in logs of the heavy over the light scale. And then remember we're computing the effective potential where all the fields have been integrated out. So then I'll integrate out the light field in the path integral, and this will give me the effective potential systematically computed in the power counting expansion. And the order to which I need to compute this, again, will depend on examples, so I'll be more specific. But the main example we'll take in this picture is I need to compute through order z to the 4th. And so this would be completely standard and straightforward, except there are several important subtleties in this procedure that mean that this actually really requires more than just the standard EFT method. So really the meat of our results and our discussion is to explore these subtleties and understand how they affect our final answer. And so this is really the interesting thing, which I'll explain today. So with that overview, so with that overview done, let me tell you what I'll say for the rest of the talk. So I'm going to spend most of the talk considering the RG improvement of a two-scalar model, which is a nice toy example for the computation and for exploring these subtleties. And I'll look at some two-scalar model with spontaneous symmetry breaking, so we can see how the minimum of the potential shifts. And make some nice plots at the end. So my plan will be, I'll need to explain this asterisk I put on the previous slide, and I'll tell you step by step. I'll walk you through this RG improvement procedure for the effective potential. And then importantly, we're going to compare our results to exact two-loop calculations. And so the two-loop leading log, the lambda log squared, is comparing this to two-loop calculations in the literature is going to be a non-trivial check of our results, and we'll find agreement. And I'll maybe end with just some brief overview of other examples we looked at and other directions you could think about. So I should mention that there's a large literature on this subject, and so there's some previous work that considered various approaches to this problem, some of which were EFT-inspired approaches, and so we checked our answer in all the examples we looked at against the literature. And so the statement is that we didn't agree with the previous literature, but we did agree with the exact two-loop calculations. So again, that's a really non-trivial check that we're doing something right. Maybe, are there any questions before I dive in? Okay. Okay, so let me introduce the example that I'm going to focus on today. So we're going to look at a model with two real scalars. One of them will be the heavy field, we'll call the heavy field chi, and one will be the light field, call it phi. And they'll be coupled with quartic interactions. So I'll have the lambda phi 4, lambda chi 4, and then some interaction chi squared phi squared. That's the lambda 3 coupling. And so depending on the parameters in this theory, you could be interested in different phases. So one thing you could look at is RG improving in the unbroken phase of this theory. So this would be a case where I'd be interested in RG improving near the classical vacuum at the origin, where both of these fields sit at the origin. And in such a case, the sort of power counting I would be interested in is when these masses, when m chi squared and m phi squared have a hierarchy. So say m chi squared order 1 and m phi squared order z squared much less than 1. Maybe a bit more interesting for our purposes is to look at the broken phase of the theory where the fields get a vev. So in this phase, suppose I'm in the regime of parameter space where both phi and chi want to get a vev, then let's call the vev at the classical minimum v. So v chi is chi at the classical minimum. It's the appropriate combination of these couplings in the Lagrangian I wrote here, and same for phi. And in such a case, I'm interested in RG improving, where I have a hierarchy of scales with v chi order 1 and v phi order z much less than 1. So here I have a hierarchy of these classical vevs. And so this is the case that I'm going to take you through right now. And our goal is going to be to compute the effective potential as a function of the background fields phi hat and chi hat expanded in this z expansion for v chi much greater than v phi, where these phi hats and chi hats, these are vevs of phi and chi, where we can start at we can give them at some high scale, some reference high scale mu naught, but then we want to compute the improvement of the effective potential at some lower scale. So I'd like to say more about this power counting. First, I need to tell you what the second derivatives of the effective potential are, because these second derivatives are this mass matrix is what shows up in the Coleman-Weinberg formula. So here I've just written out the mass matrix, and I'm going to call the mass matrix W. So the matrix components of W are just the second derivatives with respect to chi and phi. And I've written them explicitly here. The explicit form isn't so important. And the eigenvalues of this mass matrix, I'll call them M plus minus squared. The plus is because that's the big one, and the minus is because that's the small one in our power counting. And you can explicitly write what these eigenvalues are in terms of these W components. And so I told you on the last slide that we want to take some power counting where V chi is order 1 and V phi is order Z. And so this is because we want some hierarchy in these mass eigenvalues that appear in the Coleman-Weinberg formula. And so in particular, if what I want to do is I want to RG improve in a region near the classical spontaneous symmetry breaking minimum, so where chi hat squared is close to V chi squared, so that their difference is order Z squared, and same that the difference between phi hat squared and V phi squared is order Z squared, but chi hat is order 1 and phi hat is order Z. And the reason for this power counting is then I get this hierarchy of mass scales. So this is the interesting power counting to look at for the scenario we're interested in. So then the various components of W scale in this way, and the eigenvalues of the mass matrix, the heavy one is order 1 in the power counting, and the light one is order Z squared in the power counting. So then let's orient ourselves. So with this power counting, I can give you the just the fixed order one loop effective potential. So the tree level piece is just the tree level Lagrangian evaluated on the background fields. And here I've just rewritten it in the convenient way in terms of the V phi and V chi parameters. Of course, this is completely standard. And the thing I want to point out about it is that it's order Z to the 4th, because these in our power counting, these differences were order Z squared. So the tree level piece is order Z to the 4th. Then the one loop piece is the usual sum over M to the 4th log M squared, where I have the contribution from the heavy and the light mass eigenvalues. And so the heavy piece at leading order contributes order 1 to the power counting, and the light piece goes like Z to the 4th. And so the point I just want to make here is that we're going to want to compute the effective potential to order Z to the 4th in order to see the first new effects. So this is the order to which we want to compute in this problem. So this brings me to what I'll call conceptual subtlety number 1, which I want to discuss, which is, we can call it the 1PI problem, and it's very simple. So in the full theory, as we learn in our QFT textbooks, I compute the effective potential by summing 1PI vacuum bubbles in a classical background of the, in this case, with phi hat and chi hat. And so here I'm just being super explicit. What I mean by this one loop vacuum bubble, I mean this expansion in the classical background. So I have vertices that depend on the background fields, phi hat and chi hat. Remember, these entries of the mass matrix depend on phi hat and chi hat, and so they would appear in this expansion. However, once heavy states are integrated out, once I integrate some heavy states, I'm integrating out the chi, then the simple point is that information about which graphs are 1PI is lost in the EFT. So for example, I can look at this 4-point function with the heavy chi line in the middle, and this contributes to the, and this matches onto the 4-point vertex here in the EFT. But then if I look at these 2-loop diagrams, then what this means is that both of these 2-loop diagrams are going to match onto the same sort of 2-loop graph in the EFT, but one of these diagrams is not 1pi and does not contribute to the computation of the effective potential of the full theory. So, so this is the first subtlety. How do we compute the effective potential? And the solution, like the simplest solution to this, is to show that this 1pi condition on the graphs is equivalent to a vanishing tadpole constraint. And the reason to do this is that this vanishing tadpole constraint can be implemented easily in the EFT and matched in the EFT. So, so next up, I want to explain how this works. And so to explain how this works, it's useful to review the standard functional derivation of the effective potential due to Jackiw, a year after the original Coleman and Weinberg paper. And so this will set the stage for the derivation that will follow in our procedure. We're going to follow this functional derivation, and will also let us talk about some of these subtleties. So step one, shift the Lagrangian by the vevs phi hat and chi hat. So I start with my UV Lagrangian, which I wrote on the previous slide, and I'm going to shift phi to phi quantum plus phi hat, and similarly for chi. And so phi hat and chi hat are these classical background fields. And after the shift, I can reorganize the Lagrangian in powers of the phi quantum and chi quantum. And so here I'm just going to call the couplings in this shifted Lagrangian, which depend on these background fields. I'll call them like hatted couplings. So like this lambda hat is the constant, the cosmological constant. After the shift, it depends on phi hat and chi hat. This sigma hat, these sigma hats are the linear terms after the shift. They depend on phi hat and chi hat. The quadratic terms are just given by the W matrix elements, of course, that I gave on a previous slide, and so on, to up through quartic order in this case. And so for example, this cosmological constant after the shift is just the tree level Coleman-Weinberg potential, just the tree level potential evaluated on the background fields, plus whatever the cosmological constant in the UV theory, in the original theory was. Okay, so I shift, and then I want to solve for the effective action in the path integral. So the path integral in the presence of the external source, I can write as follows on the right-hand side. So basically, I shift the path integral, and the measure is invariant under the shift, so I can rewrite as just over chi quantum and phi quantum. And then what's left over in the exponent of the path integral is the shifted Lagrangian that I wrote on the previous slide, plus the source terms, which now there's the j phi times the full phi quantum plus phi hat, and same for j chi. Okay, completely standard. Then okay, we want to solve for the effective action, and the 1pi effective action is the Legendre transform of the connected generating functional, which is what's in the exponent. So these classical background fields, they're conjugate variables to the sources, j phi and j chi. And so I can just subtract off this part from this expression here and solve for the exponent of the effective action. And so I've literally just subtracted off these j phi hat and j chi hat terms. And so I'm left with an exponent, which is the shifted Lagrangian, plus the linear terms in phi quantum and chi quantum, which have the sources. And I'm going to call this whole exponent L hat. So I'm going to call this whole exponent after the shift as that we need to do the path integral over L hat. Okay, so remember, we have identified phi hat as the expectation value of phi in the presence of the source. And so the important point is after I do this shift, I need to impose that this is still true. And so I need to impose in particular that the expectation value of the quantum parts, phi quantum and chi quantum, is 0. And so I do this by adjusting the source. So I have to adjust these sources, j phi and j chi, to make this true so that phi hat and chi hat retain their original meaning. And so I can write this condition diagrammatically. Diagrammatically, this is some total tadpole. I'm putting it in green, which I need to set equal to 0, and it consists of the linear coupling. Remember, we had these linear couplings sigma hat in the shifted Lagrangian, so that gives some contribution to this tadpole. I have the j phi contribution. Remember, I still had the j phi quantum hanging around. And then I have a one loop contribution from the cubic term in the cubic terms in the shifted Lagrangian. And I need to set this whole thing equal to 0. So at tree level, evidently, well, of course, this is what we usually do. We can just set the source equal to this linear term in the shifted Lagrangian, and I'm done. At one loop level, I need to adjust the source to make this true. So we're going to impose that by setting j phi equal to the tree level piece plus a piece, which I'll call curly j, which is formally one loop order. So this curly j is the combination is being set equal to the combination of these two graphs in purple here. And so I can just rewrite these sets of diagrams in terms of a curly j, which is being set equal to minus the one loop part of this tadpole contribution, of this 1 point function. And this needs to be set equal to 0. Okay, so this is convenient, and once I do this, I can rewrite the exponent in the path integral. So I'm just going to solve for curly j in the path integral, and what I'm going to get is that this exponent in the path integral, the entire linear term in phi quantum and chi quantum is just given by the curly j, because this linear term canceled off. So maybe this seems like a lot of song and dance for a technicality, but the important point is this vanishing tadpole condition is equivalent to the 1pi condition. And the vanishing tadpole condition is something we can actually impose in the EFT without subtlety. So just for example, we can look at the two loop vacuum graphs. And if I write out all the two loop vacuum graphs in terms of this curly j, I have all of these not 1pi graphs, but if I rewrite curly j in terms of the total tadpole, then these all can just be given by a graph, which is just the thing that we set equal to 0. So this is just some example diagrammatically that the 1pi condition at two loop is the equivalent to including this curly j and then requiring that it sets the total tadpole to 0. And so the standard functional derivation of the effective potential, where I shift the fields by their background values and then just forget about the linear terms and compute 1pi vacuum bubbles, this is equivalent to including these explicit formally one loop and higher source terms and imposing the vanishing tadpole constraints on the quantum pieces. So, and again, this is the thing that's going to be useful for us to use in this in our matching. So that was conceptual subtlety number 1. So now I can talk about conceptual subtlety number 2. So I just told you that to compute the effective potential, we shift with respect to the background fields. where the background fields are the expectation values of the fields in the presence of the sources. So the simple observation is that after we integrate out a heavy field, the expectation value of the field of the light field in the EFT is not equal to the expectation value of the field at high energies before I integrated something out, and this is due to matching corrections. So the statement is, if I first shift with respect to this background field and then integrate out something heavy, this is not equivalent to first integrating out the heavy particle and then shifting. And so I'm emphasizing this because in our derivation, this means that we need to do the shift in our functional derivation at high energies before we've integrated anything out, so that because it's really important that the expectation value of phi, being this phi hat, retains its original meaning. Similarly, of course, we want the effective potential will depend on the expectation value of chi, and of course the shift had to be done before we integrated out chi. So this lets me, this brings me to our method. So here I've written some diagram of the step-by-step procedure. And so you can view this as a refined version of this super schematic diagram that I gave at the beginning of the talk. And so now I'd like to take you through step by step, where again, at the end of the day, the goal is to compute the effective potential in this example as a function of the background fields, phi hat and chi hat, at some light scale where I've summed the large logs in m light over m heavy. And so I'm computing to some order in this z, and I'm computing to some order in our power expansion. Okay, so step one is to do what I already told you we should do in the usual case. So step one is I shift the fields. So I shift phi to phi quantum plus phi hat, and similarly to chi. And I'm going to replace the sources by their tree level piece plus their one loop piece, these curly j's. And so I'm going to do this, and then the exponent that's left over in the path integral is this quantity I called L hat, and this L hat has couplings that depend on the background fields, and so it has this cosmological constant piece, which, remember, I already told you is just the tree level potential evaluated on the background fields. I'm just giving it here again to remind you what this looks like. And the linear terms now, because I did this replacement, only depend on this curly j phi and curly j chi. And these curly j's are quantities that I need to, like I said, I need to compute by imposing vanishing tadpole constraints, but I'm going to put that off until the last step in this procedure. So right now I have this L hat in my exponent of the path integral, depends on the quantum phi quantum and chi quantum, and I'm doing all of this at some high scale before I integrate anything out. So step two is I want to integrate out chi quantum and match onto the EFT. So in particular, we'll take the matching to happen at some heavy scale, call it mu heavy, mu high, which is order 1 in our power counting. And we'll match onto an EFT, which depends on the light field phi quantum. And we'll call the couplings in the EFT, which will depend, again, on these background values of the fields. We'll denote them with twiddles. So the hatted couplings are before we integrate out, and the twiddles are after we integrate out. And so for this example, I can do this by matching onto this Lagrangian up to quartic order in phi quantum that I've written here. And we need to compute these, the parameters in this Lagrangian to order, so that we've computed this, this Lagrangian to order z to the 4th, which is what we need for the order that we're considering here. So of course, the standard story is to get the leading log series, I need tree level matching of the endpoint functions in my theory expanded in the Z power counting expansion, plus one loop running of the couplings and the EFT. So just to I'll give two examples. So example number one is that this hatted cosmological constant, which remember had V tree, this goes into the matching of the EFT cosmological constant at the matching scale, mu high. Another example is the matching onto the EFT 4-point coupling. So in our L hat, two diagrams contribute. I have the lambda hat 4-point coupling in L hat. Again, this depends on the background fields. And I have this diagram with the intermediate chi quantum, which is getting integrated out. And so this diagram looks like this, and I expand for small EFT momentum. So I expand out this propagator of the chi quantum, and match onto this vertex in the EFT. I do this at the matching scale, and at the end of the day, I compute some that this coupling in the EFT is this combination of parameters in the UV theory, where or in the high energy theory before I integrate it out, where since I'm looking at this 4-point term, I only need to compute to leading order, to order 1 in the Z expansion, since phi quantum is light and goes like order Z, so this term is already order Z to the 4th. And all of these parameters are given at the high scale, so they depend on this mu high that I'm matching to. So that was two examples. Now at this point, I'd like to revisit the subtlety that I mentioned before, that we need to shift in the high energy theory before integrating out chi quantum, because I think this is a nice example of how this would come back to bite us if we hadn't done this properly. So suppose I did the wrong thing, and I first matched onto the EFT and then shifted the phi field. So let's suppose that I did things in this other order. Then I would start with this graph that I wrote on the previous slide, which we know contributes to in the matching to the EFT, contributes to this phi to the 4th coupling in the EFT. Let's call it lambda 0. It's not lambda twiddle because we haven't shifted yet. And so then suppose we shifted phi to phi quantum plus phi hat after doing the matching. So if I were to do this, then I'd have to replace I'd have terms where I replaced these phi legs with 2 phi quantums and 2 phi hats. So this matching would give some contribution to the quadratic term in the EFT and phi quantum. And so that's what I wrote here. This would give some contribution to the quadratic term at the matching scale. And there are 6 ways of replacing these 4 legs with the 2 phi quantum and 2 phi hat. So that tells me something about what this coefficient is in lambda 0. But the point is that these 6 ways arise from 2 different topologies at high energies, but before the matching. So there are 4 types of diagrams that this could have come from if I'm just tracing back to what this would have come from at high energies, where the phi quantum is on, where the 2 phi quantums are on opposite sides of the chi propagator, of the heavy propagator. And then there's 2 types of diagrams where the phi quantum is on the same side as the heavy propagator. And so, however, this sort of diagram that I wrote on the right-hand side just doesn't exist in the full theory because there's no such phi hat squared chi-quantum vertex in the full theory. So only 4 of these 6 diagrams are supposed to contribute to the EFT. And so when we do the process correctly, we get some answer where this diagram contributes to, in the matching, to the quadratic term in the EFT, and gives this particular term with some particular coefficient. And the important point is that if we hadn't done that, if we'd have flipped this procedure, we would have gotten 3 halves times this coefficient. And this would have changed our answers for the effective potential. Okay, so back to the matching. So if all I cared about were this leading log series and the effective potential, I would be done. But I told you I want to compute the full 1 loop contribution, so I also need 1 loop matching. And the 1 loop matching just comes from doing the chi-quantum bubble, vacuum bubble expanded in the Z power counting expansion. So I'm going to call this 1 loop matching contribution from this bubble, I'll call it V match. And again, we're matching at this high scale, mu high. And I can just explicitly expand out what these vacuum bubbles are to the appropriate order in Z. So they'll depend, they'll have vertices, which depend on the background fields, which come from these quadratic couplings in the W matrix. And here I'm just using some notation where the black line is the phi quantum line and the blue line is the heavy chi-quantum line. But when I do the 1 loop matching, I need to expand in the light scale. So the phi quantum lines, their propagators just get expanded out to 1 over p squared. And so the important point is that all the logs that I get from integrating these vacuum bubbles are of the form log W chi chi over mu heavy squared. And W chi chi is order 1, mu heavy is order 1. So the point is that all of the logs in this matching formula are small. There are no large logs here since I've expanded out the phi quantum propagator in Z. So just to be explicit, the particular form you don't really have to pay attention to, but just to be explicit, this will give me some contribution to the effective, to the EFT potential, where again, I'm calling this V match. And so this V match will have an order 1 piece, which came from that first vacuum bubble on the previous slide. It'll have an order Z squared piece, which came from the second vacuum bubble I had on the previous slide. It'll have 2 order Z to the 4th pieces. And then that's all we need to compute to the order to which we're working. So I want to mention for intuition's sake, so this 1 loop matching contribution, this is exactly just the expansion of the large eigenvalue contribution to the effective potential. So in the 1 loop formula, I have the contributions of the m plus squared, the heavy contribution, and the m minus squared in the fixed order 1 loop formula. And so my statement here is just if I expand out the heavy contribution, the m plus to the 4th log m plus squared, in the Z power counting expansion, this is exactly what I would get. So that's what this term is giving. And the second comment is that this whole term is independent of phi quantum. It only depends on background fields. So in particular, it contributes to the EFT cosmological constant. So at the end of the day, I can tell you what the whole EFT cosmological constant is. It's the at the matching scale. So at the matching scale, it's just the tree level potential evaluated on the background fields, plus this matching contribution, plus then there's going to be a term that depends on this curly j chi. And this would have come from the tree level matching. And the last thing I want to note about this is that this EFT cosmological constant, as well as the other EFT parameters, still explicitly depend on these sources, curly j chi and curly j chi, and these sources still need to be determined, and I'm going to just wait to determine them until the last step. Okay, so step 3 is we run in the EFT from the heavy to the light scale. So now I just use the EFT beta functions to, what am I doing? Okay, good. So now I just use the EFT beta functions to run to some light scale that's order Z. And so here I'm just explicitly giving you the two that we really need, which is the running of m twiddle squared, the quadratic term in the EFT, and the running of the EFT cosmological constant. And you don't have to pay too much attention to the explicit form, but the point I just want to point out is that this running is what sums the large logs. And so these are functions of this eta, and this eta depends on this 1/16 pi squared log mu light over mu heavy. And so they've been resummed into these etas, which happened by integrating the one loop RGE of the EFT, just defined by this EFT Lagrangian. I think I had some aside here about beta functions, but it's not really relevant, so feel free to ask me later, but I think I'll skip it right now. So step 4 is I'm going to finish the path integral, and so I've computed the in my EFT. I've run to the light scale. I have my EFT couplings now defined at the light scale, and now I just need to finish the functional integral over phi quantum to quadratic order to finish integrating out all the fields and compute the effective potential. And so this is just the so now I have some EFT Lagrangian, and this is just the standard one loop determination of the one loop determinant, and it gives me this answer. So at the end of the day, I have an effective potential given at some light scale, which is the EFT cosmological constant at the light scale, plus this m to the 4th log m squared, where the m squared is the EFT m twiddle squared, which has run to the light scale. And again, this is just from the one loop determinant from integrating out phi q to quadratic order. And again, we're only keeping terms to order z to the 4th in this expression. So this is a really simple looking formula, and I have 2 comments. So the first comment is that I think this formula is maybe deceptively simple looking. I'll remind you on the previous slide, I showed these complicated formulas for lambda twiddle and m twiddle. And so the point I want to make is that even though at the end of the day, this effective potential only depends on the quadratic parameters, the constant and the quadratic parameter in the EFT, the running required all of the EFT interactions. So it really was necessary that I compute all the interactions in the EFT. And the second point I really want to emphasize is, I would call this maybe conceptual subtlety number 3, which is this is not the effective potential of the EFT. So there is no sense in which we computed the effective potential of the EFT, in which I took this EFT Lagrangian and shifted and computed its effective potential. In particular, there's no sense in which we shift phi in the EFT at any point. We shifted phi before we matched onto the EFT. So I think this confused us for a while at the start of this project, but the point is here we're using an EFT as a tool to compute the effective potential of the full theory in this power counting expansion, with taking into account that we've integrated out some heavy field. But this is not the same thing as computing the effective potential of the EFT we constructed. So I really want to emphasize that point. Okay, Now, now we have this last step, which I told you I was saving till the end, and that is to solve for these curly J sources by imposing vanishing tadpole conditions. So I'll be a little brief here. So I'll remind you, we started this with this expression of the effective action in terms of the path integral, where the exponent in the path integral is this thing I called L hat, and this L hat had these curly J's that we inserted in, that we replaced in there, and this is what we matched onto the EFT path integral, integrating out chi quantum. And the simple statement is that even though chi quantum has been integrated out in the EFT, we can still determine the curly J chi source at the heavy scale just by doing the functional variation of this EFT path integral with respect to curly J chi, because it just explicitly appears here in the path integral. And so this functional variation is going to just give me the 1-point function of chi quantum, and I can just do this in the EFT, set it to 0, and then this will allow me to solve for the curly J's. And so I can do this at the heavy scale in the EFT, and it results in some formula which depends on the phi quantum 1-point function. It depends on the expectation value of the phi quantum squared operator. Here I'm working, I need to determine everything at the heavy scale. And this guy is just 0. And also I'll mention that I'm talking about curly J chi here because this process is just trivial for curly J phi. For curly J phi, this just gives that it's equal to 0. So I don't need some one loop correction to the phi source. So then I need to compute out this matrix element. And the point I want to make is that there's a large log. And so I need to compute this matrix element. And in particular, I need to RG improve this matrix element to sum this large log. And I do this by integrating the operator anomalous dimension of this phi quantum squared operator. So I can just compute its anomalous dimension, integrate. This gives me this expectation value I needed at the heavy scale. I plug in for curly J chi, and this allows me to solve for curly J chi. Okay, so we have some nice answer, and now I'd like to make 2 comments. So the first comment is straightforward. If I just neglect the running and compute at a single scale, then this just reduces to the 1 loop fixed order potential expanded in the Z power counting expansion. So this is a trivial statement. This had to be true if I did things correctly. If I just forget about the RG improvement and set all the scales equal to the same thing, I would have just gotten the expanded out 1 loop fixed order effective potential. The more interesting comment is that we can check our result by explicitly checking our 2 loop leading log term that we got from integrating the 1 loop RGE in the EFT and checking this against explicit 2 loop calculations to see that we did something non-trivial. And this leading log term comes entirely from the running of the cosmological constant in the EFT. And so the procedure is that I just expand out in the log that we had resummed, this log mu light over mu heavy, call it T, and then compare the order log squared term in this expansion of our result to existing fixed 2 loop order results expanded, which also need to be expanded in Z to come to the appropriate order. And the result is that we get perfect agreement. And the thing I just want to emphasize is that all the subtleties I brought up throughout this talk were crucial to getting this agreement correct. And so I'm going to end with showing you some fun plots now. So I've computed the RG improve effective potential, and I can ask what happens to the minimum. So to do this, let's just choose I chose some starting values of the parameters at some high scale. And in particular, I chose my, my vevs, v phi and v chi, my classical vevs, to have some hierarchy, which is, of course, what we're interested in. And so just to orient you with these choices of parameters, I can plot the effective potential as a function of phi hat and chi hat. Here I'm showing some slice with chi hat equals to its tree level value, just so I can show you a 2D plot. And there's something a little interesting that happens, which is with our input parameters satisfying this hierarchy, v phi much less than v chi, then there's some numerical instability where the one loop order z² terms in the matching, the one loop matching contribution overwhelm the tree level potential, which was order z to the fourth and the order z to the fourth terms. So here I'm just writing out this one loop matching in terms of its order 1, order z², order z to the fourth pieces. And so this order 1 piece is just a constant. It doesn't depend on either phi hat or chi hat. So this is just some large constant, which is the cosmological constant problem, and we can just subtract off from everything and call that done. But this order z² piece is some large compared to the z to the fourth pieces, not constant. It depends on phi hat and chi hat. And so this is the fine-tuning problem rearing its ugly head. And in our case, a simple fix to this hierarchy problem is just to make a judicious choice of matching scale. If I choose the matching scale as such, then I completely cancel off this whole z² column, and I don't have to worry about this. Of course, I could choose the matching scale to be whatever I want it to be, as long as it's of the right order in the power counting expansion. And then I make some nice plots. So here I'm plotting the effective potential as a function of phi hat on a slice where I've chosen chi hat to be its value at the full RG improved minimum. So with these values of all the starting parameters and so on that I told you on the previous slides. So the blue is the tree level potential. Its true minimum isn't quite what's represented on this plot because, like I said, here on this plot, I'm plotting everything for the slice where chi hat is at its full RG improved minimum, which isn't quite tree level minimum. And so we can compare the tree level, but here I'm showing where the real tree level minimum is, which remember we set at 247 GeV. So I can compare this first to the one loop fixed order answer. So at one loop fixed order, I would have found that the minimum shifts all the way out here by about a factor of 2. And of course, we didn't expect that one loop fixed order was reliable when I have a hierarchy like this. And indeed, if I include the RG improvement, actually it shifts the minimum of the potential much closer back to the tree level minimum. So it still shifts the tree level minimum. The full RG improved minimum is now at I forget, it's like 317 or something GeV. So it's still a shift from the tree level minimum, but it brought it back closer to the tree level minimum as opposed to the less reliable one loop fixed order answer. So there's some noticeable effect here from resumming these logs. And then I think I've gone a little bit over time, so I'm just going to end with some comments on other things we did and other things we can do. So in this talk, I told you about how we about this procedure for RG improving the effective potential with this with such a hierarchy, and I told you about this 2-scalar example in the broken phase, but we've computed the RG improved one loop potentials in several examples and found agreement with 2-loop fixed order in all cases. So we looked at the 2-scalar theory in the unbroken phase. We looked at the ON model in its broken phase, where I have like Goldstone modes and a heavy radial mode. So it's a very natural hierarchy in that case, because of course the Goldstone modes are light. We looked at a Higgs-Yukawa model where I have some fermion and boson coupled with a Yukawa coupling, and the boson has a mass and a lambda phi-4 coupling, and in such a case, I could look at a hierarchy where the fermion's much heavier than the boson, or the boson's much heavier than the fermion. So these are both interesting cases. And here I've written the power accounting that would be relevant to having a hierarchy in the Coleman-Weinberg potential for each case. We also looked at a complex scalar coupled to a fermion, which was an interesting test study to see that our result has no Goldstone boson IR divergence, which just makes contact with some of this previous work, but I'm not going to say more about that. And so this is what we did, and looking to the future, I think, so first of all, there are some obvious generalizations that you can do. So it wouldn't be, so our formalism, you could extend to the gauge case. We only looked at examples that weren't gauge theories just because there are some subtleties with interpreting the effective potential in the gauge case, but our formalism works perfectly well for the gauge case. So you can do that. You can go to higher order. So you can do in whatever example you like. So you can do one loop matching two loop running to go to next to leading log order, for example. You can look at higher derivative terms in the effective action. And for me, what would be really most interesting is if this formalism was useful in some example where it taught me something fundamentally new about the structure, about the vacuum of the theory. So I first got interested in this problem when I was working on some SUSY breaking and some model which had nothing to do with any of this. And I wanted to know if the one loop corrections told me something new about the minimum of the potential. And I realized I couldn't say anything because I didn't know how to compute the potential reliably at one loop in that case. And so I haven't solved that problem yet, but I think it would be really interesting if this was applied to some example where it could tell us some new physical effect. But I don't know, that's just some speculation. And so thank you for your attention.